Okay, we're recording now. So today, what is going to be our final lecture on new material. Normally, what I would have done for next week would have been I would have had a final review on the Wednesday and then just not had class on the Thursday. So I think I will still have some. I guess we'll have some kind of review, something or other on Wednesday. We'll normally have we'll have some type of review, something or other, but I may just record it and post it and not have you guys come and meet on Wednesday. Probably what we'll end up doing. But I do want to cover a couple of things. I'm going to go ahead and share now. Okay. Yep. I'm going to go ahead and share this because I've had a few questions about this that's due on Monday for assignment 4. So I had to make an edit. If you have an old version of this document, then you have this whole customer, add customer, and get customer. It had club customer in there, but then up here I say remove that class. It was just a typo on my part. I forgot to change this to customer. So from now on, we won't have a special class called club customer that represents a customer inside of a store. It was kind of, if you think about it, it was kind of not really a convenient class for us to have anyway, because what happens if somebody is a club customer at Migros, but they're not a club customer at A101 or Carrefour, something like that, right? We want the stores to have their own groups of customers that they keep track of. So now, basically, a store will have some type of collection that represents their list of customers, where we can access them using their phone number, because I'm sure, as many of you have probably experienced, as soon as the person at Migros, actually I just went there this morning, as soon as they start scanning your items, they ask you, do you have a card? Are you a club customer? Like, do you have, are you in our system? And I tell them my phone number, and they find my information in there, and then hopefully I get some kind of discount or something. We didn't have any type of discount stuff here, and so anyway, so let's see. So that's what I expect you would do, is you'd have some kind of collection here that tells me what customers are associated with that store. Let's see, some other questions that I wanted to address that I thought were interesting and good questions. You were asking, somebody was asking, well, how do I add a product? How do I add a product to my cart? Well, so if you think about it, I'm a customer, and I could be ordering stuff from Migros online, like through Sunall Market. I could also be trying to order things at another store. Let's see, my wife had ordered from Migros the other day. She also ordered from, where else did she order from? Macro Center, right? So she also ordered from Macro Center because they have lots of nice gluten-free things. Because she can't eat things with wheat in it, right? So we want to have separate carts for that, right? We don't want to add to cart stuff that we expect to get from one store into the cart for another store. So what you could do is you could have a collection. The customer could have a collection, and the key could be what store they're adding the collection for. And then the value for that store could be a collection of products and the number of products that the customer is getting from that store. So, for example, you have maybe a cart collection, right? And the key is store. And when I access that store, so let's say the key Migros. When I go to Migros, what I get returned is some other collection of products and the number of those products. So let's say Migros, I'm getting chicken, I'm getting Snickers. Of course, I always get Snickers. I love those things. What else do I get from Migros? Let's see. What else do I get from Migros? I don't know what else. Just Snickers and chicken. I don't know. So cola, I get cola. Okay. So when I pass access with the key Migros in my cart, what I get is a returned collection of products that I'm getting. So chicken 3, along with Snickers 25, and what else did I say? Cola 1, right? So these are the types of things you might do there, and looks like good. I'm glad we're interacting. I'm glad we're getting this interaction thing going, because it looks like we have a question over here. Let's take a look. Question in the store class. Normally we have a remove customer method. Oh, so okay. Basically what I said was write and modify, right? So what that means is anything that I didn't list specifically, it should stay as it was, right? So what was let's take a look. Assignment 3. No, assignment 3 is the software dev assignment. Let's go back to assignment 2. All right. All right. Store. Remove customer with their phone number, it stays the same, right? Now, what that means is that for the store class here, I should still have a remove customer that takes a phone number, and what it does is it removes, what did it do here? It removes the customer with that phone number from my collection, from my set or my collection or my list or whatever data structure you use for your customer collection here, it should remove that customer from that collection. Okay. And it should still, if that phone number is not found, it should still have that customer not found exception. Okay. So does this mean that the method itself will stay the same? Probably not. What it means is that the definition of this method stays the same, but how you make it happen might change, especially if you change here, if you change what type of set you're using or what type of collection you're using to store customers in your store, then you may have to change how this method removes them from it. Okay, I hope, is that clear, Suleiman? I think, Suleiman, you messaged that, right? That the definition of the method will stay the same. You still need to have the method there. Anything that's not explicitly listed here, anything that's not specifically listed here, just maintains its previous definition from the previous assignment. Okay? Nothing changes about how it's defined. Let's see. Okay, good. All right. So I think that covers most of the questions that I felt were very important, and I wanted to go ahead and address live in the lecture. So there's a couple of other questions that are specific to specific students that I'll be addressing those within the day. So, all right. So let's move on back to sorting. All right. Let's see. We finished off on the bubble sort, and we were going to go into merge sort. Okay. Now, the idea behind merge sort is it's actually something very similar to how I might sort. Remember, the example I keep coming back to is if I were to give you a set of exam papers or a set of quiz papers or something like that, and I wanted to sort them by some type of criteria like student number or let's see, another question? Nope. Okay. Like some type of like student number or name or something like that. So as I'm sure that you realized with the bubble sort and with the insertion sort, those would get the job done on a set of papers. But in something like a set of papers where you have like 100 set of papers, it would be very time consuming. It'd take a long time for me to go through all 100 papers and find the earliest name or student number and put it to the front, and then search through 99 papers and find the next one, and then 98 papers and so forth. That would take a long time, right? So what I usually do when I have like a list of papers or a set of quiz papers or something like that, what I often do is I kind of just divide up the stacks into smaller stacks. So let's say I might take 100 papers and I might divide it into 4 stacks of 25, and then I might sort those 25 on their own. And then what I'll do is, my wife and others who have seen me do this when I'm doing this at home, it's like I'll sit there on our salon table and I'll have these 4 stacks that are all sorted, and then I'll just go through and I'll look through the top stack, the top page on each stack, and I'll say, oh, which one's the earliest out of that? Okay, grab that, and then I'll grab the next one. And maybe if any of you might think it might be humorous, I might video myself doing this sometime, so that you can maybe laugh at me, but also get an understanding of what I'm describing here. And so what I do is I merge those stacks together. What happened to the computer? What's going on? Okay, are we still here? Are we still on? Okay. My computer just blacked out for a second. Is everything still on? Looks like it. Okay. All right. So anyway, so I'm merging them all together into one stack. And so this is basically what merge sort does, is we take our stack of values and we split them into smaller stacks, smaller arrays or lists. I say stacks. I know stack is it's an actual data structure, and so I'm misusing it. It's not really a stack. It's an array. But I think you guys understand what I'm talking about. Recording? Yeah. So sorry. I don't know what's going on. It's trying to update right in the middle of our lecture. All right. So we take this smaller array and we split it off. Right, and we take this smaller array and we split it off, and then what we do is we say, okay, now I'm going to take this, I'm going to split it, and I'm going to split it, and we keep doing that until, in this situation, we get down to an array of one, a bunch of arrays of one value. All right, and then what we do is, this is a sorted array, this is a sorted array, this is sorted, this is sorted. All of these, since they're only one value, they're all sorted. Right. So then we take our small array and we merge back together. But when we merge, we don't merge it back into the same way it was. That wouldn't make sense. So what we do instead is we merge it back sorted. So we take the smaller of the two values and we put it first, and the larger and we put it second. And we do this in each situation. Notice here 5 and 4 becomes 4, 5. 8 and 1 becomes 1, 8. 6 and 7 becomes 6, 7. And then we do it again. We merge this array of 2 with this array of 2. So which is we look at the first value in each situation. 2 is less than 4, so 2 comes first. Now we don't compare 5 and 9 because we're still looking at 4 over here. 4 hasn't been moved into our big array yet. So we look at 9 and 4. 4 is less, so it goes next. Now we look at 9 and 5. 5 goes next. This array is completely done, so we don't need to look at it anymore. 9 moves here. Okay. Over here, same thing. 1 and 6, 8 and 6, 8 and 7, 8 and nothing. And then the same thing, we do it again here, but now instead of merging 2 arrays of size 2 into an array of size 4, we're now merging 2 arrays of size 4 into an array of size 8. So 2 and 1, 1 goes first. 2 and 6, 2 goes first. 4 and 6, 4 goes next. 5 and 6, 5 goes next. 9 and 6, 9 and 7, 9 and 8, 9, and nothing. Okay. So this is the way we merge. We merge them back together into a sorted array. All right. So basically, if you notice, the sounds of, I'm sure some of you may have kind of already thought this as we were talking about it. Hey, this kind of sounds like it could be a recursive definition, right? Notice what we did. We took the big array and we split it into 2 smaller arrays, and then we did that again, and then we did that again. And for each sub array, we did the same thing as we did before, right? So the merge sort can be done as a recursive definition, where we take the first half of an array. When we're merge sorting some big array, all right, we take the first half and we merge sort the first half of the array. So at the end of this call, we're going to have the first half of our list merge sorted. We're going to have the first half of our list sorted. Then at the end of this call, we're going to have the second half of our list sorted. And then what we do is we simply take the first half and the second half and we merge them together for an overall list. And then we return this. Okay? So is that clear how that's working out? I'm hoping as many of you, I would be looking for the look on your faces right now if we were in a classroom environment to see if this was like, what are you talking about? Okay, but basically the idea here is we take the first half of our list, we sort it. We take the second half of our list, we sort it, and then we merge those two together into an overall list. And then notice that no matter how big this list is, we can always divide it into half until it's only one item, of course. All right, we can always do this smaller and smaller and smaller until we end up down to one item. So we can do this through a recursive definition. All right. So see, this was kind of how this works, right? So we have a pointer, a current index for each subarray, and then for our overall array. Okay. So as we merge through 1, 2, 4, 5, 6, 7, 8, 9. Right. So as we all right, so we merge them down in 1, then 2, then 4, then 5, and we keep this current pointer, we keep this index of where we are in each spot, okay? Because it's what's the next value that hasn't been processed in our subarray, okay? So what's the time on merge sort? Well, as our name of our lecture today implies, both of the algorithms we're going to look at today are nlogn, okay? And basically what happens is we need to look at the time that it takes to merge, to sort each subarray, and then the merge time. So if we have a size n array, then it should take the same amount, but the same time, but n over 2, right? Because we're going to sort n over 2 items, plus the time it takes to sort the other n over 2 items, plus whatever the time is to merge the two together. Now, so then the question is, what's our merge time? How much time does it take to merge the two items together? Well, to process through n items, processing through, notice that we just visit each item one time to put it into its correct position in the overall array. So that would be n. It would take n, some multiple of n time in order to fill this overall array. Okay, so that's where we get this big O of n from. So then the question becomes, what about this part? Well, a lot of big math stuff here that basically, as we determine this whole 2 to the k, and you'll get into all this a lot more in depth in your algorithms class next year. Right? But what ends up happening is that because it is a divide and conquer algorithm,
You can't
Yep.
see this screen.
What's going on? What do you see?
Can't see the screen.
Ah, wait a second. Okay. Okay, let's try that again. I wonder if when the computer, can you see it now?
Yes, thank you.
Okay, good. How long has it been like that? Okay. Let's see. So here, yeah. So anyway, basically, because it's a divide and conquer algorithm, it ends up becoming a logarithmic thing. And there's this whole mathematical proof. For those of you who are really like math and stuff, you could look at this and then have a good understanding of this. But your algorithms teacher will go into this in a lot more in depth. Okay. For why this is nlogn. All right. So that's merge sort. We'll take a look at that. So you have a conversation. Okay. Yeah, I think what happened was my computer did some weird hiccup thing when it tried to update, and I think what happened was it killed the sharing of the screen for some reason at that point. So, okay. Oh, okay. I should know. We'll look at that in the example. Okay. What we'll do is we'll pull up. I have an example over here for us to look at, and we'll take a look. Okay. All right. Good question. All right. One other that we'll look through in the slides here before we go to the examples is we'll see the quicksort. So the idea is similar to merge sort in that what we do is we sort a subarray. We sort two subarrays and then put them together. All right, but the difference is that what we do is we have a pivot point. All right, so if this was our original array and we want to sort this, we take the first value and we call it the pivot, and we say everything smaller than this we're going to put in front of the pivot, right? And everything larger than this we're going to put behind the pivot. So what we do is we start at the next position, and if this thing is smaller than the pivot, we leave it here, right? And if this thing is bigger than the pivot, we put it back over here instead. So notice that at the end of this, we have 5 as our first pivot. The value is the first pivot. And notice that here, 5 goes right here, and everything to the left of 5 is smaller than 5, and everything to the right of 5 is larger than 5. Right? So then if we look at this as our new subarray, our new partial array, right, our pivot is 4. Everything to the left of 4 is smaller than 4, and everything to the right, well, there's nothing to the right because 4 actually ended up being the largest value in our subarray. Okay. Then our pivot is 0. We end up in a similar situation for this subarray. All right. 0. Everything to the right is bigger. Everything to the left is smaller, but there's nothing to the left. For this new 3-element subarray, all right, everything to the left is smaller. Everything to the right is bigger. And this ends up being sorted. And notice that when this gets put back in with this, 0, 1, 2, 3 is sorted. And then when this 0, 1, 2, 3 gets put back into here with 4 on the end, it's sorted as well. And then when that 0, 1, 2, 3, 4 gets put back into here, 5 will come next. It's sorted also. And then we're going to do the same thing on the right-hand side also. Okay. One of the big problems with the quicksort, as I'm sure you could see, actually, let me go back to this slide, is that if the pivot we choose is on the end, right, then we kind of processed through a bunch of items and didn't really do anything. We took a lot of time to do nothing, right? Because we still had to process through each item. Because when we look at this right here, 4, 2, 1, 3, 0, and our pivot is 4, 2, 1, and 3 all got left where they were, but we still had to visit them and check. Is 2 less than 4? Yes. Is 1 less than or greater than 4? Less than, so it stays. 3 less than 4? Yes. 0 less than 4? Yes. Right, so, and then we just swapped the 2 out. Okay, so if we choose a bad pivot, if our pivot is either very high, like towards the end over here, or very low towards the end over here, then what ends up happening? We process through, we visit all these values in that subarray, but we don't really do anything. So it's just a lot of work for no gain, right? In the case of choosing this pivot 5, we divided it into 2 pretty equal subarrays, and it really helped out. It really made the what is it? It really made the work less for us that way. Okay, so in the case of Quicksort, this gives us an interesting insight into its worst case situation. The worst case of Quicksort is we keep choosing pivots that are either very high or very low in terms of the rest of the values in our array. It's not necessarily that it's already sorted, it's just that we choose high or low values. Okay, so one solution to this is that sometimes in choosing the pivot, we don't just choose the first value in the array, and we don't also just choose some random value in the array. What some implementations of Quicksort will do is they'll choose what's called the median of 3, where what it does is it looks at the first value in the array, it looks at the last value in the array, and then it looks at some middle value in the array, and it says whichever one of those, the middle of those 3 values. So in the case of this, we would have 5, 4, and 7. We would choose 5 as our pivot, giving us a greater chance of choosing something that's towards the middle of the overall array. Okay, so for an example of here, we would choose 4, 1, and 0. And then we would choose the median of that, which would be 1. So yeah, we still would get only 1 value smaller and 3 values greater, but at least we wouldn't be in this worse situation of having 4 values smaller and no values greater, right? So it gives us a guarantee that the value we choose is not the lowest value or the highest value in our array, and that therefore there's a greater chance of being able to divide it somewhat equally. Best case analysis, best case situation for Quicksort is you constantly pick a pivot that is right in the middle. That is a value that's right in the middle of your overall array there. Okay. All right. So again, Quicksort. So if we want to look at how this works, the pivot is, so this is our high, this is our low. All right. What we do is we keep looking until we find a value that's higher than our pivot. So 2 is lower, so we move up to 9. So then we go up to the high pointer and we keep looking until we see a value that's lower than our pivot, that's smaller than our pivot. 7 is bigger, 6 is bigger, 1 is smaller. So now look, now we have a situation where we have a value in the array that its position is earlier than a value in our array where they should be swapped, right? Where 9 is bigger than 5, it should come over onto this side. 1 is smaller than 5, it should come over onto this side somewhere. So what we do is we just swap them. So we don't do a lot of movement. We don't do a lot of movement, like we don't say, oh, 9 is bigger, move it into the last position. We don't do that because it's not about necessarily finding the biggest value in the array that's bigger than our pivot. We just want everything that's bigger to go over here to the right side. We want everything that's smaller to go over here to the left side. So we find a smaller value here, a bigger value here, we swap them. Okay, so now let's keep moving. 3 is smaller, so we move on. 8 is bigger, we hold. Okay, 9 is bigger, 0 is smaller, so we hold there. So now we have 8 and 0. we need to swap them. They're in the wrong position, right? So we swap them. 0 and 8 get swapped. Okay. Now low, 0 is smaller, we move on. 4 is smaller, we move on. 8 is bigger, we hold low here. Okay. So for the high points at 8. We keep 8 is bigger, we move on. So now look, now we have high pointing at this position, low pointing at this position. The pointers are opposite now. We've crossed paths. We've reached the place where everything in this position and down is smaller. Everything in this position and up is bigger. So what do? We swap now 5 with our smaller of the two, right? So we put 4 over here into the pivot spot. What was the pivot spot? We take 5 and put it into this spot. And now look, the pivot is here at 5 and the index of this spot is returned. Okay. So now we have our pivot value is sitting right here, and everything to the left is smaller, everything to the right is bigger. But notice that everything to the right, to the left is not sorted, everything to the right is not sorted. The only thing we have right now is a pivot point where everything to the right is bigger and everything to the left is smaller. That's the only thing we have. But as we take this smaller array and we do the same thing again, we're going to end up in that same situation, right? Where everything to the left is smaller, everything to the right is bigger. And if we keep doing that over and over again, eventually we're going to have all of our subarrays sorted where all of our pivots along the way, everything to the left is smaller, everything to the right is bigger. And what that's going to do is it's going to sort the overall array entirely. Okay. All right. So to partition an array, it takes n-1 comparisons. So the time required just for partitioning, right, is going to be n. So this is kind of like the merging. The partitioning is kind of like the merging. In terms of it, there's a big O of n aspect to the quicksort. But just like with the merge sort, the dividing and doing the same thing again, the divide and conquer aspect ends up making it log n. That part is log n. Okay. So in the worst case, each time the pivot divides the array into one big subarray and the other empty. We looked at that. We saw that in this example here, right? Our pivot chosen was 4. We still had to do it with n-1 items here and 0 items here. That's our worst case, which basically what ends up happening is quicksort, if we constantly choose a bad pivot, if we constantly choose an endpoint as our pivot, then what ends up happening is quicksort becomes one of our, like an insertion sort, right? So we don't want to do that. We would like not to choose a pivot that's on the end, which again, one solution to that, to help with that, is to do this whole median of 3, where we look at this, we look at this, we look at this. Oh, we look at our endpoints and our middle point, and we decide on the median of those 3 values to get a guarantee that we're not dividing into one n-1 array and one 0 size array. Okay. And the choosing of the median of 3, look at this value, look at this value, look at this value, that's constant time. It is extra time to do that, but it's constant. We always know how long it takes to do that. It doesn't matter the size of n. Okay. So best case ends up being n log n, right? The best case pivot divides array evenly into 2 parts. Right, so notice this becomes the same formula as we saw for the merge sort. It becomes n log n. All right. So again, the exact average case analysis is not for this class. That's going to be your algorithms class. So look forward to that. And we won't go into the rest of these, but I encourage you to look at them if you're interested in some of these other sorting algorithms. One of my favorites is the heap sort, and so if you look at it, enjoy that. It's a very interesting topic, and like I said, you'll cover that in your algorithms class next year. All right. So let's take a look at our two sorting examples. So if we look at this, so this will be our initial array here. All right. So what we do is, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is going to be an even size array, but it's going to divide into two odd sized arrays. So I think, Aishanur, I think this is going to cover your question of what you were asking, right? All right, so I want to do this through the canvas so that we can see how this works. All right. So our size of our list here. Okay, so our list is here. Okay. All right. All right. So if our list size is greater than 1, why do we need to check if it's greater than 1? Because if its size is 1 or even 0, then we don't need to do anything. It's already sorted. We don't have to do anything. Okay. So what we're going to do is the first thing we're going to do is we're going to copy into the first half our list. Notice here, look, it's the first half. So again, this is a size 10 array, right? This is a size 10 array. So we're going to take the first 5 elements and put them in here. Okay. So then we're going to merge sort those 5 elements. We're not going to worry about the other 5 for right now. We're just going to merge sort the first 5. Okay. So I want to look at this one. We're going to see how this works. Okay. Because notice this was our 10 size. This is our that size. Okay. We're going to copy again the first half of size over 2, right? So size of length over 2. Well, its length is 5. So what is 5 divided by 2 using integer division? I hope some of you heard in your head 2 is 5 divided by 2 using integer division. So what happens is for our first half, we just take the first 2 items. So notice that here, if I see what this size is, notice it's just the first 2 items. Okay. Now, why the first 2? Well, because for an odd size array, what we need to do is we need to divide it into an even size and an odd size, right? We need to divide it into an n over 2, rounded down size array, and an n over 2. Oops. Could we have done it? Could we have done it using the other side instead? Could we have done it a 3-value array on this side and a 2-value on the? Sure, of course. That would have been a valid solution as well. It doesn't matter whether the first half is bigger or the second half is bigger. We just have to take this middle value and put it somewhere. It either needs to go in the first half or the second half. Okay. So in this implementation, we put it in the second half. So we take the first value here and goes. All right. Let's see. So we keep going. Okay. Because now our list is size 2, right? Here. So now we're going to have a list length over 2, right? So what's 2 divided by 2? Okay, that one's easy. I hope it's easy. So it's just an array of size 1. So now we're just going to take it. It's just 1. We're done, right? This is already a sorted array. Okay. Now, for this second half, we're going to make it the size, the list we passed, minus that length over 2. It's going to be the other set of values, and we're going to copy the array into there. All right. Copy array into second half. So what's second half? It's also a 1-value array. All right. Because this was our original list. Our first half is 2. Our second half is 3. Right. So since this is also a one value array, it's also done, right? Okay. So then we're going to merge them together back into here, right? Notice what the merge does. The merge doesn't return anything. The merge just uses this original array as a temporary location, okay? And it pushes them back into there. Now, this one's not as fun to watch because it just ends up being with the same values, okay? Okay. So I'm not going to look at the merge on this one. I want to look at the bigger, this one would be a good one to watch, I think. Okay. All right. Okay, because now what we have is what? This is our list. This is our first half, and this is our second half, right? Okay, 2, 3, 2, 5, 6, 2, 3, 2, 5, 6, right? So this was our merging these together, all right? Okay, so let's take a look at how those merge together. I'm going to look at them inside of here. List 1, list 2, and then temp. Okay, because we're going to see how these get put into here. Okay, so current 0, current 1, current 0, current 2 is 0, current 3 is 0. So we're looking at the very first position in all three arrays right now. Okay. Now, while current 1 is less than the length of list 1 and less than the length of list 2. Basically, what this loop is going to do is, as long as there's still stuff to process in either of the two lists, we're going to keep working. We're going to keep looking at the two of them. But once one of these two positions, once either this is exhausted or this is exhausted, we're not going to continue looking at both of them because we don't need to. As you're going to see, once list 1 is done, once we've already put 2 and 3 into those correct positions, we don't need to look at list 1 anymore. We just need to take the rest of list 2 and put them in the end. It would be like, for example, back to those quiz papers example. If I had a stack of quiz papers and I'm merging them together and I've completely exhausted all of the papers from one of those stacks, right? The stack of papers. I don't need to continue comparing anything. I just need to take all the rest of the other stack and put it on the very end, right? Put it on the back. Okay. Yeah. The more I think about this, the more I think I am going to record a video of myself actually doing this with quiz papers, because I still have a stack because I never got to return them because I was going to return your quiz papers and then we stopped a meeting in person. So, all right, so I think I'm gonna do that. Okay. All right, so anyway, current 1. So we're pointing at here, we're pointing at here, and we're pointing at here. Okay. All right, if this is less than this, we're going to put the thing from list 1 into our position. If otherwise, we're going to take the thing from list 2 and put it in this position. Now they're the same. So is it less than that? No. So we're going to take the thing from list 2. And so we're going to take this and put it into here. Okay. All right. So now we're going to move on into our temp list. We're also going to move on into our list 2. Now, is 2 less than 5? And the answer is yes here. So now we are going to take the thing from list. Notice now it changed, right? This got copied into here. So this 2 got moved to here. This 2 got moved to here. Now we're pointing at 3 and 5. Which one is greater, 3 or 5? Hopefully you said 3, right? So 3 is going to get put into here. Now, current 1 is not less than the length of list 1. So we're done with this while loop. So now we're going to come over here. Now, is current 1 less than the list of length 1? Now, the reason why we have these loops here is because you might say, well, of course not. This isn't true. Why did we even look at this? We're done with this. When we get done with this loop, we don't know which list was done. We don't know whether we were done with list 1 or we were done with list 2. The only thing we know is that one of them is done. So if it was list 1 that was exhausted, this will not be true. This will be the reason this loop ended, and we'll just skip over it. If the other one was the reason why we exhausted, the list 2 was the reason we exhausted, then we'll end up skipping over this instead. Okay, so now what we do is we skip over that. So now what we do is we just take the things from the end of the list 2 and we move them to the end of our array here. So 5, 6, and we're done. All right. Okay. So now what we have, all right, is we have the first half of our array sorted. All right. Okay. So now we're going to do the same thing with our second half, and I'm just going to skip over that part because we'll remove all this stuff. Okay. So the second half is going to work the same way. It's another 5-element array. But now if we look at our first half, it's a, all right. First half is sorted, second half is sorted. And if we go to merge them, this should be the same array as that, and this should be the same array as that, so this should work. Okay, so now we're just going to go through. What's less, -2 or 2? -2. Got it put up here. What's less, 1 or -1 or 2? 1. What's less, 2 or 3? 2. What's less, 2 or 3? What's less, 3 or 3? This 3. All right. Okay. Now what's less, 3 or 12? 3. Now what's less, 5 or 12? 5. Now what's less, 6 or 12? 6. And we're done with list 1. All right, we're done with this. This is done. So we skip over it. Now we just take the 12 and the 14 and we push them into here one at a time. And we're done. Now we have a sorted array. Okay. All right. And then if we wanted to display all our items here in our sort, there it is. Okay. So this is the way merge sort would work. And if we now look at the Quicksort version of this, all right, here, now we're going to choose just the first pivot, I believe. All right. All right. So the way that, one thing I want to point out here about the merge sort versus the Quicksort implementation, in the merge sort, notice that every time that we went to do the sort of the first half and the second half, we created a new array, right? That's kind of the problem with the merge sort, is that it requires another array be created. So for very, very large arrays, think about, we're creating a new array of size n every time we're sorting and merging, every time we're dividing and merging, right? With Quicksort, we can use the original array and we never have to create another array. Okay, we just create the pivot and we then move the stuff around by swapping the pivot, by swapping the values before and after the pivot, and then we end up with in the original array the sorted values. Okay, it's a little bit makes Quicksort can be a little bit better because not only is it nlogn, but it also doesn't require extra memory requirements for us to create all these extra arrays. Okay. All right. So Quicksort, right? We're going to choose a pivot index using the partition of the list and the first and the last. Right. So this is all right. So we're going to partition them first. We're just going to choose the first element to be our pivot, so 2. All right. Low is in this position 1. High is whatever the last position is. All right. 9 over here. All right. Is high greater than low? While that's true, keep going. Okay. While low is less than or equal to high, so as long as we're still looking at the values before the high value and our list is less than or equal to our pivot, well, that's a problem already, right? Low list of 1, 3 is not less than our pivot. So we just skip over it. So now we're going to keep looking here until we reach a value that's less than our pivot value. Okay. 12 is less than 2. 12 is greater than 2. Good. We keep going. 14 is greater than 2. We keep going. 3 is greater than 2. We keep going. -2. Hold on just a second. All right, sorry about that. So where were we? -2 is less than 2, so we have to stop. Right now, we have found a position where something is in a position that is less than something else, but the values they're out of order. Right? -2 should be somewhere earlier than 3. So what do? Okay, we swap them using the swap technique, right? So we swapped them. -2 is now here, 3 is now here. Okay, but are we done? Have the high and low pointers crossed paths? And the answer is no. Okay, 2 is less than or equal to pivot, so we keep moving. 5 is greater than pivot, so we stop. Oh, low didn't change from that. So now 5 is greater than pivot. Okay, so now we're pointing at 3. 3 is greater than pivot, so we keep going. 1 is less than pivot, so we stop. So now we're looking at 1 and 5. So we swap those two. All right. So now what's our low and high value? Let's see. Low is 3. So we're looking at the value 1. It's less than our pivot, so we keep moving. 6 is greater than our pivot, so we stop there. High, we're looking at this value. 5 is greater than our pivot, so we keep moving. 6 is greater than our pivot, so we keep moving. Now we've gotten a situation where high is less than low. So we've crossed paths. So we're done. High is greater than low. Sorry, if high is greater than low, which it's not. So we skip over this if statement. We back out of this while loop. Okay. All right. So now, if the pivot is greater than our list at high, is it? Yeah. We swap them. We swap 2 with 1. So then we return this index as where our pivot is. Okay. So now what we have is we have a pivot index. There it is. It's about to be created. There. Pivot index of 3 here. And everything above it is equal to or greater than this. Everything below it is less than or equal to it. All right. So then what we do is we take these three values and we do the same thing. So let's just take a look at one more set through here. Okay. Look at those three. So we're going to partition them. So first and last is 1, -2, 2. 1 is our pivot. And so now what we're going to do is we're going to end up, are we going to swap these two? No. All right. It's already done. All right. It's already what we needed it to do. High becomes that. We don't swap them, but what we do is we are going to move this into this position. All right. And so now what you'll see is we have these three values in sorted order. So now notice that everything up to our original pivot now is sorted. All right. And we do the same thing with this side as well. And when we do it with both sides, we end up with a sorted array. All right. I think you all got a notification just now about the quiz 2B. So I'm not going to keep you for much longer. I want to give you as much time as possible to work on that. But I do want to end with this thing that I want you to note, is that if you look at these different sorting algorithms, notice that merge sort and quick sort are faster. They're nlogn than insertion sort and bubble sort. All right? Nlogn for these two, n squared for these two. Right? But also notice that merge sort is a lot more complex, right? Quick sort is a lot more complex. Insertion sort, pretty straightforward, pretty simple, right? Same thing with bubble sort. It doesn't take a lot of code. It doesn't take a lot of complexity to write these to make them happen. That is the trade-off that we often experience in writing our programs, is that to make something better in terms of runtime or in terms of memory usage or in terms of some resource, using less resources to make them happen, what ends up happening is a lot of times the writing of the code has to be more complex. Right? And so that's our trade-off, is that oftentimes in order to make something run better, we have to spend more time developing it. And I'm not going to say which one is better or worse, because it's not like that. There isn't a better or worse or a right or wrong. All four of these methods, all four of these, and heap sort and the others over here as well, they all sort arrays. They all do the same thing. They all result in the same situation. I could pass this array into any of these methods and it would end up giving me the same result output. They're all correct. The question is it worth it for me to spend that extra time developing to get something that runs faster? Sometimes yes, sometimes no. Okay, so I want you to, if you're still thinking that there is a right answer to everything, I'm kind of wanting you to get out of that mindset, okay? Because there's multiple correct solutions to the problem here, okay? All right, so take a look at that quiz. You have until 1:30 to get that done, and like I said, I'll try to record kind of a final review, final words of advice from me to you for your final exam thing that we're going to do. And other than that, it's been a great semester. I regret, I'm sad that we haven't been able to see each other in person for most of this semester, it feels like, and definitely miss all of you guys. So, but hopefully we'll be back to normal in the fall. All right. Have a good summer break, and Ramazan bayramınız kutlu olsun. All right. Thanks, guys. I'll see you whenever we are able to see each other again.